Hello everyone, my name is Gregor Weiss. I'm a professor of finance here at Leipzig University, and welcome to this video on artificial intelligence and machine learning in finance. Now in this video we'll have a look at the k-nearest neighbors and the Bayes classifier in order to classify observations based on training data and to predict into which class, for example, new test observations will fall. We'll later on look at support vector machines, but in this video we'll start out with the k-nearest neighbor classifier. Now if you recall the classification problem, we are always led to the question, how can we assess the model accuracy of a given classifier? That is it able to classify a new observation correctly, or does it classify it into a wrong class? Well, this is obviously in contrast to regression methods, where we've already seen measures of model fit, and it's clear that for classification problems this looks a little bit different. So we'll start with the training error rate, and this is done for qualitative responses, for example, default, non-default, or contract termination, no termination. And the training error rate, and with this we mean the proportion of mistakes that the algorithm has made if we apply our estimate f hat to the training observations. This is defined as basically the average of an indicator function. This is I here in line at equation 21. This is an indicator function that looks at the comparison of the observations yi of our qualitative response, and it is 1, the indicator function is 1, if yi is not equal to our predicted value. So yi hat is the predicted class label for the ith observation, and we simply take the average across all these indicator functions. So basically, again, it's the proportion of mistakes that we make. So this is the training error rate, and this is done for the training data. So in time series terminology, we would say in sample, and then it's clear that we can also look at the out of sample predictive performance, and this here in statistical learning is called the test error rate. So the test error rate looks at the model accuracy of a classifier when the classifier that has been fitted is applied to new data. And the test error rate, now again the proportion of mistakes that we make if we apply our estimate to the test observation or test observations x0, y0, again is defined as the average of a comparison of the responses y0 and whether we can actually predict it correctly or not. So it's the percentage of incorrectly classified test observations. And naturally we are looking for classifiers that are able to reduce both the training and the test error rate, and in many cases we will see that the algorithms are not able to generalize well to new data. So you have a high in-sample fit, a low training error rate, and a rather high test error rate. So what would we use as a classifier? Well, the most basic classifier is the so-called Bayes classifier. It's the classifier that assigns each observation to the most likely class given its predictor values. So we assign a test observation with predictor vector x0 to the jth class, for which the conditional probability that y is in the jth class, given that we've seen the predictor values x0, so that this conditional probability is largest. In this case, the test error rate is minimized on average by our Bayes classifier, but this is only theoretical, and it's actually only of any use in theory, because the problem is, for this to work, for the Bayes classifier to use, the distribution of y, the conditional distribution of y given x, of the response given the predictor values, it needs to be known. And in practice, this is never known. If we knew the conditional distribution of y given x, we could simply estimate and calculate these conditional probabilities, and then we would know which predictors predict our outcome. But this is not the case, so we cannot actually use the Bayes classifier in practice. So what we can do instead, and the k-nearest neighbor classifier is closely related to the Bayes classifier, we start with the positive integer k, for example, 5 nearest neighbors, 3 nearest neighbors. So we have an integer 5, k, and one test observation, x0. And starting from this test observation x0, we identify the k points in the training data that are closest to x0, and we call this n0. Then we estimate the conditional probability. Note that this is not known ex ante, but we can estimate the conditional probability for class J as the fraction of points in the set n0 whose response values equals j. So the probability is estimated simply by taking the average of the indicator functions when looking at the observations in the vicinity of x0 that belong to class J. And this is why it's called k nearest neighbors. You take the observation x0, you look at the k, for example, the 3 closest nearest neighboring points, and you see, for example, if we have a 5 nearest neighbor classifier, and we observe that the 5 nearest points to a test observation are belonging to, let's say 1 is belonging to the class and 4 are not belonging to this first and only class, then it's 1 out of 5, and this is our estimated conditional probability for class J. We then apply Bayes rule and classify the test observation x0 to the class with the largest probability, because we've now estimated these probabilities. This is what comes out of the actually the Bayes decision boundary. As you can see, if we know the conditional probability, the conditional distribution of y given x, then it's actually quite it's actually the best classifier we can achieve, because we know the conditional probabilities. And you can see with 2 classes in yellow and purple, yellow and blue, and the purple line is the Bayes decision boundary. You can see that, for example, if we have a new observation that would fall in here, we would classify it as the blue class. If it falls in here, then it's classified as the yellow class. And this could be default, non-default, contract termination, no termination, etc. With k nearest neighbors, it works like this. We have this point, for example, and we take the 3, if it's k equal to 3, the 3 nearest neighboring observations, 1 blue, 2 blue, 1 yellow. So this area is considered to be in the blue part, and this is where it will now appear here. So this here is, for example, the blue class, and we now do it again here. So it would probably be 1, 2, and I would say this is the 3rd point, so this is also blue. And this is how you construct the decision boundaries. And what happens is you get obviously a nonlinear classifier, nonlinear classification boundaries. And this is 3 nearest neighbors. You can also use 5 nearest neighbors, 10 nearest neighbors. With the simulated data, obviously, with so few observations, it doesn't make any sense. So this is k nearest neighbors. How does it compare to the Bayes decision boundary? Well, you can see here we've used 10 nearest neighbors, and you can still see the Bayes decision boundary in purple. It is a little bit more wiggly. As you can see here, it's close to the Bayes decision boundary, but it is a little more variant. As you can see, it has more variance and less bias. Okay. Same picture, but now for k equal to 1 and k equal to 100, and you can see what happens with k equal to 1. It gets even more wiggly here, and with k equal to 100, it's very coarse. It's a very coarse, even linear decision boundary. And again, you can see here the bias variance trade-off in play, and k is obviously a hyperparameter that needs to be chosen before applying the algorithm, usually via cross-validation, to arrive at an optimal algorithm.